So I'm Ioana Ifrim, and as Vasil mentioned, I will be presenting today the work regarding GPU acceleration of automatic differentiation in C++ with Clad. The way I will go about this presentation is I'll firstly discuss the motivation behind this work, then automatic differentiation and applications on a machine learning case study. Then I will talk about Clad AD plugin for Clang, and the C++ compilation pipeline, as well as the Clang compilation pipeline in the Clad context. Next, I will present the GPU-accelerated AD work in terms of implementation features and benchmarking. And finally, I prepared a demo of using Clad and CUDA as a service with Clang, just before concluding with a summary of the work status and future steps that are ongoing and that will be taken. So in terms of motivation in mathematics and computer algebra, automatic differentiation is defined as a set of techniques used for numerically evaluating the derivative of a function that is specified by a computer program. So it is an alternative technique to symbolic differentiation and numerical differentiation, the method of finite differences, and has applications ranging from machine learning area of domains to high energy physics. And the aim of Clad is to provide automatic differentiation for C++, which works without code modification and includes legacy code. And the range of AD applications are defined by their high computational requirements and thus can greatly benefit from parallel implementation on GPUs. And looking into a use case of machine learning application, here we would use gradient descent to update parameters for a chosen model. And the training inputs are fed forward and they generate corresponding activations. And we defined an error that is the difference between what we expected as output and what was labeled in the original data. Difference between this and the model computed output. And the error adjoint is then propagated backward, resulting in the gradient with respect to the weight. And this procedure is basically the central player of the gradient descent optimization algorithm. And the required gradient is obtained by this backward propagation of the sustainability of the objective value at the output, using the chain rule to compute partial derivatives of the objective with respect to each of the weights. And in this way, the resulting algorithm can be interpreted as transforming the network evaluation function composed with the objective function under reverse mode automatic differentiation. This is a generalization of the backpropagation procedure. So as mentioned before, there are a number of alternatives in the way we can do this. We can do differentiation. Historically, it was the case that machine learning researcher would dedicate considerable amounts of time to the process of manual derivation of the analytical derivatives, which were in turn used in gradient procedure. This work method, despite being very time-consuming, is also highly error-prone. And then another alternative comes into the form of numerical differentiation, which is the finite difference approximation of derivatives using values of the original function evaluated at some sample point. However, this comes along with the introduction of round-off errors, spawning into issues of consistency, convergence, and stability, as well as making it a non-suitable option when it comes to processing very large dimension gradients, such as the ones that are usually used in machine learning and where they can reach order of millions. Another option, symbolic differentiation, is the automatic manipulation of expressions for obtaining derivative expressions. And it is carried out by applying transformation representing rules of differentiation. Practically, symbolic differentiation can easily produce exponentially large symbolic expression, which take correspondingly long time to evaluate. And this problem is known as expression swell. And also, it may require transcribing the result back into code. Now with automatic differentiation, this can be defined in our case as automatic differentiation of a C++ program able to compute the derivative of a given function, where this procedure involves applying the chain rules of differential calculus through the semantics of the original program. So one example of a use case in machine learning could be, for example, fitting a logistic regression model by minimizing the binary cross-entropy loss of the logistic output. And in this example, we decompose the gradient into gradient components of the individual transformation path, starting with the pre-activation and their gradient with respect to the parameters and activation. In automatic differentiation, we identify two modes. The first of which is the forward mode, where we start from the leftmost node and move forward along the rightmost node in the computational graph. And here we obtain one derivative with respect to an input parameter with every forward pass. This can be achieved in Clad, for example, by calling Clad differentiate and the name of the function and the name of the variable, where the forward mode automatic differentiation for Clad is guaranteed to have at most a constant factor more arithmetical operations compared to the original function that we started from. In the second mode, called the reverse mode, we start from the outermost node and move backward. And this is particularly useful in machine learning applications because these tasks involve a large number of feature space parameters who need to be tuned. And this means that the reverse mode AD fits perfectly into achieving this task of calculating the derivatives for the cost function with respect of such parameters. So in Clad, this can be achieved by calling, for example, Clad gradient with respect to the desired function that we want to compute the gradient for. Clad is a compiler plugin extending Clang and is able to produce derivative in both forward mode and reverse mode, as I mentioned. And it supports derivatives partial and higher order, as well as gradients, Hessians, and Jacobians. And it also provides low-level derivative access primitives, and it allows to be embedded into frameworks. The typical C++ compilation pipeline has code going through to the compiler front-end or back-end and resulting in output binary. Alternatively, when we add plugins into Clang, the tree representation of the abstract syntactic structure of source code gets passed onto the plugins, and then further on after processing to the Clang backend with the result of the binary. Now the same principle applies to Clad as a plugin into Clang, where the abstract syntactic tree is passed onto Clad, and it results into finally a binary or code for the process function as a result of either the forward or the reverse mode based on our choice. Okay, so now putting everything into context, in the use case presented here, for example, in machine learning, as I said, the goal is to compute the gradient of the cost function with respect to some transformation parameter vector. And thus, from an automatic differentiation perspective, this can be done by either invoking the forward mode and computing the derivative for every dimension, or the most efficient way by invoking the reverse mode and having all the computation done in just one single pass. And these passes are bounded by access to and computation performance transformation parameters. Hence, this process is an excellent candidate for acceleration through GPU support implementation. And In general, tasks featuring heavy computation increase their time consumption proportional with the dataset magnitude. And this application can thus profit from the usage of threads. In this sense, GPU acceleration brings basically a new layer of optimization and the proportional speed up. So the CUDA support for Clad includes extensions that allow one to execute functions on the GPU using many threads in parallel. And function attribute cloning has been introduced for device or host to be carried forward in the Clad gradient definition. As well as custom derivatives were extended to include these attributes declaration, as well as dependencies on the standard library functionalities that were not supported by CUDA. These were re-implemented. Failing by contrast, the template library for CUDA based on the standard template library has proven for us particularly to be an issue in the context of Clang compilation. Moreover, Clad uses tape records for the execution that is replayed such that the gradient is produced in one pass. This also required some extension for the CUDA context and removal of the dependencies that I mentioned on the standard library. And how it all played out, I have some benchmarks that are shown here and illustrate how using CUDA can influence the overall automatic differentiation performance in computation. On the left, it's for a Gauss gradient with different dimensions, and the same on the right, but for a product function. And we can see that for high dimensionality, the GPU overall time, which includes the kernel computation time, as well as the memory transfer from host to device and vice versa, show better performance in terms of speed. And this particular benchmark was done on a Tesla with 16 gigabytes and on an Intel Xeon CPU. What is worth mentioning here is, for example, the right-hand side plot is done with a bit of improvement in terms of GPU scheduling. So we can see higher gain on speed up. Whereas on the right-hand side, on the left-hand side, the Gauss gradient didn't have the most optimal GPU scheduling. But even so, the time speed up is observable. Okay, so the way CUDA options can be used at this moment is the following. The desired function to be differentiated needs to be declared and appended with device host attributes. And the signature of the, in our case, gradient function needs to be declared, and it follows the naming convention from Clad, that is the name of the original function underscore grad, with the return type void and an extra result argument, which will store the result coming from this. And this function will have its body generated by Clad, and we can use a device function pointer to keep a reference to this. Afterwards, the global kernel calls upon a function pointer, which we later send it as such, and performs the execution of the gradient function. We then define our variables on the host side and copy them to the device for passing them onto the compute kernel, followed by copying the results back from the device to the host. And all this procedure was also the one used in the benchmarks, making use of the NVProf, which was the tool used for the plots. And this enabled the collection of a timeline of CUDA-related activities on both CPU and GPU, including kernel execution, memory transfer, memory set, and CUDA API calls and events or some metrics for CUDA kernels. Okay, so in terms of using Clad and CUDA as a service, I have a demo that basically shows the Clang usage of Clad as a plugin to produce a derivative on the fly, and then to send it to CUDA kernel for execution. Okay, so including the Clad plugin, and then as I mentioned before, we need to define the our function that we want to produce the gradient for. And then we call clad gradient on this function, which will define the body of here the big Gaussian PDF grad, which will then be used in order to execute the computation on the compute kernel on the GPU. So we copy from the host to the device in order to use the variables, and then call the compute, and then copy the result back. And we can see the result computed on the GPU. And this is basically the code that came out from Clad for the gradient of the function that we defined. Okay. Clad can also be used as a service. It can be used within the Jupyter notebook with the help of Xeos Clang. This is a Jupyter kernel for C++ based on the C++ interpreter Clang. All you have to do is have Clad installed and pass it as attribute to the kernel as a plugin to Clang. And then you can easily include it and use it to differentiate for forward mode, or to use it for the reverse mode to compute the gradient. And this can all be done interactively. Okay, so as a summary, the generated Clad derivatives are now supported for computations on CUDA kernels. And this allows basically for further optimization. Given that scheduling still requires a certain degree of user input, we are working now on further automatizing this. And Clad can now handle hybrid GPU-CPU setup, where for now the generation is currently done on the CPU, the generation of the gradient or derivative, and the execution can be parallelized on GPUs. And there were a few challenges. I will briefly mention some that I mentioned before, actually. With the CUDA version, Clang and Clang compatibility can be observed in implementation choices, for example, not relying on trust, and implementing whatever needed support from trust, re-implementing so that we can avoid that. And this was fixed. And passing the gradient function by pointer when compiling with Clang is working nicely. However, in Clang, we're still working to fix this and be able to pass the gradient by function the gradient function by pointer, and not specifically calling it. So in terms of future steps, one goal is to implement full support of arrays. Forward mode support was already implemented and merged by BiDeNet, and reverse mode is in progress. Development is in progress. Furthermore, in our interactive use case, we aim to provide an API which synthesizes the CUDA kernel automatically. And this will basically alleviate the user's need to deal with memory optimization. and enable automatic differentiation support for second-order derivatives for HEP through root, that is the data analyst software package via Clad. This is in progress as by the GSO project. And currently the scheduling procedure, as I said, requires some input. And we are now working on trying to fully automate this step for complete CUDA integration. So the toolchain process will need to be formalized with both scheduling optimization and global memory constraints in mind. Thank you.